Welcome to another 5-minute quick tips video from Mentor Graphics, where we will be discussing the mesh technology available in FloEFD. For our first example, we'll be looking at a 2D aerofoil section called the RAE2822, which is a very common wing profile used for benchmarking CFD software. In the Creo parts tree, we can see the actual wing geometry in green and also a transparent enveloping body called mesh, which we'll be looking at shortly. Looking at the computational domain, we can see that this is an external flow analysis which is being solved in 2D. The size of the computational domain is user-defined here and the 2D option already selected. Let's now have a look at the base mesh settings. The default mesh settings in FloEFD are controlled by an automatic mesher. This will look at the geometry present and apply a series of presets it deems appropriate. We can overlay the base mesh onto the screen and move the slider bar to preview the mesh at different levels. As we can see, FloEFD uses a Cartesian mesh to solve the finite volume Navier-Stokes equations. We have the option of disabling the automatic mesh settings and using a manually defined mesh. This gives the user access to the number of cells in the X, Y and Z directions and also the control planes, which stretch the mesh to achieve a coarser grid in the far field away from the action. In addition to the base mesh settings, we can use the local initial mesh option to manually apply additional grid in areas or volumes of interest. As I mentioned earlier, we have a mesh part which overwrites the wing profile. We can use this volume to apply a local initial mesh. Let's turn off the automatic settings and force the mesher to refine the mesh up to level 3 within the volume using the slider bars. We'll discuss mesh levels shortly when we come back to look at the mesh. The final aspect of the meshing technology in FloEFD is the solution adaptive meshing capability. This allows for the automatic refinement of the mesh in high flow gradient areas in the solution. Again, based on a level system, we can restrict the software on how small the grid cells can be. The mesh density will increase only in areas which are required, which makes for a very efficient mesh. Let's now have a look at the mesh created. The first is the default mesh created using the base settings plus our local initial mesh and has approximately 35,000 cells. The local initial mesh region can clearly be seen around the wing section. In the far field, we have very large grid cells away from the lifting surface, and closer in they get smaller in the user-defined region. On the actual surface of the wing, we can see even smaller cells which have also been manually defined. The mesh system in FloEFD works using levels. The base mesh is referred to as level 0. Octree meshing technology means that a single cell is then split into 8 cells to go to the next level up. We can see level 2 grid cells in the mesh region and level 3 at the walls. At this stage, no solution adaptive meshing has occurred. Loading in the next mesh, we have an approximate count of 150,000, about 5 times as many. Showing the cut plot, we can see the mesh refinement which has occurred. We can now see a spread of level 3 grid cells in our mesh volume and some level 4 cells at the wing surface. The mesh refinement also occurs in the wake zone behind the wing to capture these flow gradients in higher resolution. The final mesh has over 580,000 grid cells, which is a significant jump. Level 4 grid cells can now be seen at the leading and trailing edges as well as the shockwave location on both surfaces of the wing. Finally, showing a contour plot of Mach number shows a nice crisp shockwave as a result of our high mesh count. In the second example, we'll be looking at a 3-way water valve. A cross-section shows the internal flow region in the valve. The valve angle is controlled by the MCAD system, and under these conditions we would like to know how much of the flow entering from the left of the screen passes across the valve and how much gets diverted at 90 degrees. By showing the base mesh, we can see the automatic settings which get finer as we move to the right. We then apply solution adaptive meshing and set a maximum cell level, in this case level 4. The first mesh is adequate for an approximate result with up to level 2 grid cells. The second mesh is finer with cells up to level 3. The final mesh, after 2 sets of solution adaptive refinement, can be seen with level 4 cells. Coarse areas can be seen in the inlet pipe, but much finer around the diverting valve. One of the main benefits of having this refinement technology is that it effectively becomes a mesh sensitivity test. By running the same geometry with a series of differing meshes, we can be sure that the final result we get is accurate and mesh independent. This is very powerful and a big time-saving feature for users. Users can start with a coarse mesh and let the software iteratively refine the mesh automatically to achieve an accurate solution without being a meshing expert or prior knowledge of the solution. This has been a quick 5-minute FloEFD overview from Mentor Graphics. Please look out for our other videos.